Okay, and this delta math, just wanted to give you guys a little guidance on it. So I'll do a little few of them on each level here. If you want to watch this, you can. I think I'll give you some pointers here that'll make it a little easier for you. Okay, so here we got these different locations and different relative masses of the planets, different relative radiuses of the planets, and we're supposed to rank them in order of their gravity force at that point. Okay, so would be my suggestion. This made it easier for me. The mass is in the top of the equation, so 3m goes in the top. I'm talking about that g(mm) over r squared, right? G(m1), m2 over the d squared. You know, I'm not going to do that whole equation out, but I'm going to say, hey, basically the mass doesn't get squared. The distance does get squared, so I take this 2r and square it. It's actually going to turn into 4r. Maybe square it, I don't know. You should put that on there, but basically I'm looking at this coefficient 3/4. This one we got 2m in the top, and then when I square the bottom, I'm going to have again 4r, capital R actually, right? Squared, capital R. And then this one, the m and r are just normal, so it's just m over r squared. So this is just 1, right? So we got 2/4. This is actually a half. And we've got 3/4 over on that first one, and then we've got 1. So if I order those from least to greatest, we're going to go 1/2 is the smallest, 3/4 is in the middle, and then 1 is in the top. Okay, let's do another one. Okay, so I'll use that same strategy. I'll put the m in the top, and then I'll square the r in the bottom. That's 9. Mostly just worried about this number here, this 1/9. Okay, this one will be just a 1 in the top and an r squared in the bottom. So that's just 1 over 1, or just 1. And this one is an m in the top, 1m, and a 4, right? If I square this, 4r squared in the bottom. Okay, so I'm comparing just the coefficient in front there. Basically, this is 1/4, this is 1, this is 1/9. Obviously, this is the smallest, 1/9. The middle one would be this 1/4, and the greatest is 1. So I would just suggest using that method, especially if you're having trouble. You can maybe just look at this and get the answer without doing that, but if you need a method, that's what I would do. I feel like that section is almost harder than the other ones, because these other ones I found easier, I thought. So activity 2. They're giving you kind of the same scenario: relative radiuses, relative masses of the planet, the gravitational field at each location, or at one location compared to the other. Okay, so I was able to do this without writing out all my work, actually. I mean, these are the same, so really the mass is 2 times bigger here. That's going to make the gravity force 2 times bigger at B. That seemed pretty obvious to me. This one, radiuses are same, so again, radiuses are same, so that doesn't affect it, but the mass here is 3 times bigger. Mass is just in the top, it doesn't get squared, so we just say straight up mass or if you're on planet B, the gravitational field strength, which is basically how much it would pull you, is going to be 3 times bigger, because 3r doesn't affect it, right? Because they're the same. I'm just looking at 3m compared to m, 3 times bigger at B. Okay, let's do one more. This one, they changed both, okay? So it got 3 times the mass for this planet, and it's also twice as far away. So if you think about it, you're gonna do 3 in the top, but 4 in the bottom, is that right? So it'll get 3 times bigger because of this, the force, the gravitational force or the gravitational field, but it will get 4 times less. So we're talking 3/4. This gravitational force is actually 3/4 of this, which means this one is actually 4/3 of this one. Okay, if this one's 3/4 of this one, that means this one's 4/3 of that one. Okay, let me go on to that last section there. Okay, and this one is more a little calculating the exact value. Gravitational field strength at this point is 10 newtons per kilogram. It's kind of like the field is kind of like the acceleration there. Honestly, it's like at that point it's going to be a 10 newtons per kilogram. That's like 10 meters per second squared actually is what that is. So you'd weigh 10 newtons for each kilogram. That's like on the surface of the earth, right? 9.8 newtons for every kilogram. Determine the field strength at Y. It's getting twice as far away. That's the key. So basically when you get twice as far away from the center, your gravitational field will get 4 times less, or divide by 4. So I need to do 10 divided by 4. 10 divided by 4 is 2.50. It does say give it to the nearest 2 decimal places. Okay, let's do another one. At this point, the gravitational field is 8 newtons per kilogram. We're going 1, 2, 3 times farther away, which means it will actually get 9 times less. So I take that 8, but then I divide it by 9. 8/9 is, I think, 0.88, right? So to the nearest tenth is 0.89. Okay, that makes sense. Yeah, let's do one more. Okay, at this location, it's 1.72 on this planet. It's obviously not Earth. It's like the moon, roughly. And we're going 1, 2, 3 now. So we're going from 1 to 3. That's a factor of 3 times farther away, which means the force, the field, which is like the acceleration, actually, will be 9 times less, right? So we're going to take this 1.72, and I'm going to do 1.72, but I'm going to divide it by 9 again, 3 squared. Okay, I get 0.19. Let's check that. Well, I screwed something up there. What I did. Another one. I think this might be a similar one. What did I do wrong? Okay, so here it's 1.72. Oh, I see, it's backwards. At this point, it's 1.72. And now I've got to go to Y, so it's actually going to get 9 times. So we're going from a radius of 3 to a radius of 1, factor of 3, but with the radius you square it, so it's actually going to be 9 times bigger. That's what I screwed up there, I think. Gave me the same problem again. 9 times 8. I'm sorry, down here. 1.72 times 9 is 15.48. Let's try that. There we go. Okay, so you do gotta be a little careful. This one again is telling me the gravitational field at here is, can't see it up there, 1 point, where did we go? Oh, up here, 1.05. We're getting 1, 2, we're going from 4 away, 1, 2, 3, 4, down to 2 away. So it's 2 times closer, which means my force will get multiplied by 4. 4.20, if I did my math right in my head. All right. Okay, so hopefully that makes sense there. Get all 3 sections done there, guys, is your assignment for today.